Okay, let's go with some of the questions people asked since last time. Okay, and that's going to take us to the rope model of light and gravity. Okay, and one person says, since your rope hypothesis conveniently doesn't need to be proven, what makes it better than all the others? And what's rational to you may not be rational for others, right? Or vice versa. Invisible threads are certainly no more rational than an invisible ether. Well, there's two questions. The first one is whether it's got to be proven. Proof is religion. Proof is in the pudding. Proof is what my whiskey has. Okay, that's proof. Okay, in science we don't prove. We don't do verification. We don't do falsification. We don't do any of that nonsense. We don't believe in science. Okay, it's in religion where we believe. In science we explain objectively. What is objective? Objective is what comes out of the screen or from the event itself, the actual event. That's what's objective, what comes out of there. What you interpret, that's subjective. And what you believe in is more subjective still. Okay, so that's the first issue. Second issue is whether the threads, the fact that you can't see them. Well, this is not a question of seeing. The question is whether a thread is a physical object and whether the ether is a physical object. Okay, that's what we have to solve. And ether is not a physical object. It's not a medium. No such medium called ether. But if you think ether is a medium, all you have to do is draw it, illustrate it. And there, that's the illustration you'll find for the luminiferous ether. When you do a Google search, you want to do some other type of search, do it, no problem. I just need a picture. Show me your ether. Okay, and you can take the earth out of there, you can take the moon out of there, the little circle out of there. Just show me the ether. I want to see what the ether looks like. Just show me the ether, and then we'll know it's a medium. Because a medium is that which has shape. Okay, if you don't like that definition, then you got to start a little lower and say, what is a medium? What is a thing? What is an object? Okay, those are synonyms in physics, but if you have a different definition for them, hey, be my guest. Come here and tell us all about it. We'd love to hear your definition of object, of thing, of medium. Okay. Okay. So what is he talking about? What is this rote nonsense? Okay. Well, here it is. Okay. This is what these folks. Here you have Fresnel, Faraday, Fizeau, Foucault, and Maxwell. All these people, Hertz and others as well. And this is what they work with. And you look at that and say, well, what the hell is that? And what you're seeing is an abstraction. What you're seeing is a bunch of vectors. That's what those arrows are. And those arrows are vectors, which means that each arrow represents magnitude and direction. Magnitude being math. Direction is a qualitative thing that doesn't belong in math. I can't put direction in an equation. Okay? I can put a number there, but I can't put in a direction. No, direction doesn't belong in math, okay? And so they have magnitude and direction for the arrows, which, again, means that you're talking about an abstract mathematical concept which they call mathematical object, right? And those arrows make those two, the red and blue squiggly things there, which are called fields, and two fields make the electromagnetic wave. That's why it's called. One is electric and the other one is the magnetic. And so what is this nonsense? Well, this can't be a mediator, just like ether can't be a mediator because, they're talking about abstract concepts until you can illustrate it. Here they try to illustrate it, but what they have is arrows representing numbers. And so, yeah, this is not an illustration of a thing. This is not a medium. This cannot be used as a mediator in physics. Okay, so if you thought this was bad, here they put it in motion. Here it is. Look at this. Now it's in motion. They put all these numbers in motion, these arrows. That's what all those up or down lines are. Okay, and they're moving sideways. It's very scary stuff. What do you mean? The numbers are moving. The numbers and the directions are moving sideways. So very scary stuff. I tremble when I see this. Okay, so what do we replace it with? Well, this is what we're replacing it with. We're saying that what they've confused all these years is a rope for what they call an electromagnetic wave. Okay, that was the error that they made all these years. Okay, and yeah, when we put it in motion, you can see that we have two different mechanisms. Okay, here it is. Okay, well, one goes sideways one way only, the other one twirls in place, goes nowhere. Okay, so we're saying that the light is a rope, okay, mediated by a rope, and the rope twirls in place at great speeds, right? Such that, we can explain now why light is so fast, because, it goes nowhere. Essentially, it's a rope that twirls in place. And so what we receive at the ends are the thumps on the atoms that are connected to that rope, the rope that interconnects any two atoms out there. Okay, so that's the story. Very simple stuff, baby stuff, really. Okay, and you can see why they confused it with the rope, because, why they mathematized what they weren't supposed to mathematize, which was trying to turn a rope into what they call vectors and what they call fields, what they call waves. None of those are part of science. None of those are part of physics. Physics, you need objects, and a rope is an object. So when people say, Bill, all you did was give a new name to the fields. No, a field is a concept, bunch of numbers in space, different values at different points in space. That's what a field is, meaning it's a mathematical concept. It's not an is nothing, right? It's not an is, it's a concept. And threads, here, thread, that's an object. Okay, these threads, that's an object. That's a thing. That's the difference. Okay, so what's our basic system? Well, here it is. Two atoms, like good old Richard Muller said, bound by another electromagnetic rope. Not a wave, not a wave packet, not a bunch of photons traveling from one to the other. No, it's a rope that interconnects any two atoms. And the atoms are made of the same threads as the rope. So the threads turn into the atom, which turn into ropes, which turn into atoms, and so on down the line. Okay, very simple stuff, really. Our universe is a very simple place from a physical standpoint. Mother Nature, Father Universe never went to school. They never studied math. They know nothing about math or about relations. All they do all day long is move one atom from, one location to the other. Throughout the universe, every atom just moves from one location to the other. That's how simple our universe is. Not as complicated as people want it to be. You have all these atoms, they're within space. What is space? Well, space is not it's not a container. We have no other language to talk about space, really, but space is nothing. What is nothing? That which has no shape. And nothing, space, vacuum, is the opposite of object, thing, medium, which is that which has shape. That which has shape against that which doesn't have shape. Now we have definitions we can work with in physics. Okay, so here's the rope atom. It looks something like this. This is our atom. Okay, that's what it looks like. Okay, and you have all the ropes from every atom in the universe converging upon our atom, and the ropes build our atom as well. Okay, so that's the simple universe in which we live. We have all the atoms in the universe, and they're all interconnected by ropes to all other atoms in the universe. That's the model, very simple model, really. Okay, so one fellow asks the following. He says, what is the rope made out of? Well, I hope it's very clear. It's made out of two threads, two strings, two wires, two fibers, whatever you want to call them. There's two, a red and a blue, I call them threads, wound around each other like DNA. What's the problem? I thought that was straightforward, and this guy never saw a rope in his whole life. And so you might say, Bill, you're making fun of him. He's referring to, what is the ultimate thing that makes up these things? And the answer is, when you give me a lazy question, means that you haven't even done a minimum of thinking, I'm going to give you a lazy answer. Okay, so I'm giving them a lazy answer. It's made out of two threads, period. Okay, when he uses his brain, I'll try to use mine. Okay, does it occupy space? Space is nothing. There's nothing. Nothing means it has no shape. That's what space is. Vacuum, nothing. All those words mean the same thing. Zip, emptiness. Okay, and so if space is nothing, you cannot occupy space like your rubber ducky occupies, your water in the bathtub, displacing it. Okay, so by occupy, we usually mean displacing. Like what is volume? Volume is how much water you displace. That's what volume means. And you do not displace volume of space because space ain't a thing like it is in mathematical physics. And that's where the problem starts, because these people made space into a physical thing, then united it with time, which is not a thing, but they made a bigger thing, a fourth-dimensional thing, and now nobody even knows anything about anything because they just put it beyond your reach. You cannot even imagine space-time. Okay, so another fellow asked the following. He says, when will you notice that a two-piece rope is always 180 degrees opposed and never 90 degrees opposed like the EMR? Okay, so what is he saying? He's saying that if you look at the electromagnetic wave, the electric thread or the electric portion field, right, is at that point 90 degrees to the electron. The electric one is opposing the magnetic one. And the issue is that, what have we been doing all these years? Well, we've been simulating with that nonsense there, which is the electromagnetic wave, right? Two fields made of vectors. What is that? And so what we're saying is, really it's, when you have everywhere you look at a rope, right? You have, like if you look at it straight ahead, right? You have one right opposite the other. And that is your 90 degree there, right? So even if you take this out, you're going to end up with something like that, okay? Where one is opposite the other. So, this whole thing needs to be reevaluated under the rope model because they've never pondered the rope. They just thought about waves and particles primarily, and they've got it, they misconstrued the entire universe because of this. Neither the atom, neither the mediator of light, or the alleged mediator of gravity, none of them have anything to do with reality. That's the issue. So if you have the wrong hypothesis, the wrong assumption to begin with, if that's what you build your edifice on quicksand, well, yeah, it's going to crumble. That's the situation. Okay, so here we have another fellow, and he says the following, why does the thread form a rope instead of just going through itself? Is it because maybe the threads are going in opposite directions? Well, this is a valid question, okay? This is a valid question because the fellow is asking, says, look, you say that thread ropes, they go through each other, right? So why do they form the rope? Why doesn't the red one here blend with the blue one, or go through it or whatever? That's the question. And, all I can do is tell you, let's first put it in the right context. What he's saying is it has to do with the assumptions, with the properties of the rope, okay? We're not talking about theory here. We're talking about the hypothesis, the assumptions that we make about the rope. And all I can tell you is my assumptions, okay? Whether you like them or not, those are my assumptions. And I pointed out the other day that, you have like two pieces of cotton. I didn't do it with cotton. I did it with bathroom tissue, okay? And so, here you have one thread. Let me get rid of this so that we can see it better. Okay. So here we have, one bathroom tissue, and here we have another one, right? And they're wound around each other, right? And you can see that as long as you kind of pull them outwards, they don't blend against each other. But if you take these two cotton or bathroom tissues, right? And you have guy hold one end, two ends, and the other guy hold the ends of the other piece, and you go through them, one is going to break or both of them are going to break, right? That's going to be our experience. And so there's a difference between going through when it goes at a certain speed and a certain force, right, that you apply to it. So, it's got to do with velocity, one. It's also got to do with how many, because like in the case of magnetism, you have all these threads, moving in there, okay? They're banging against each other. So this one attracts the other guy. And let's see if I got this one. I think it's this one. And this one repels the other one, right? So you can see that the force is from inside, okay? The fact that it's pushing the other one away shows that there's something in there. It's not from the outside here. It's from the inside, okay? That's the first thing. But then there's something there, and I'm saying it's all these threads pushing against each other. And you say, hold it, how come they're pushing against each other when they should be going through each other? And again, it's a question of aggregate, the fact that you have gazillions of threads, they're threads, not ropes. You have all these gazillions of threads pushing against each other, so you have many of them. That's one issue. The other one is, yes, there is a tiny friction when they go through each other, except that when you have two threads, imagine how thin they are, the ones that Mother Nature works with, unimaginably thin, okay? And so the question is, how do they go through each other? Well, they go through each other because, first of all, they're thin. That's how Mother Nature or Father Universe made the universe. And here, let me give you, for instance, an example, okay? Look at this. Here's the Earth, and imagine a little thread, and that's a very thick thread, right? Because you can see that compared to the Earth, it has a certain thickness. But imagine gazillions of times thinner than what you see there, right? That's the first thing. Just try to imagine that. I can't illustrate it for you because I would have to illustrate just a small portion of the Earth there, and that's what I will do next. But just right now, I just want you to think of that thread, or that rope really, right? Being extremely, extremely thin. It's invisibly thin, okay? And so here you have we're going to replace the Earth with an atom now, okay? So it looks more or less like that, okay? Think of it like that. But again, the thread is much, much thinner, or the rope is much, much thinner than what I show there, okay? So what happens when we zoom in to this picture, the rope converging upon an atom? Here it is. Okay, this is more or less what it looks like. And we're going to be zooming in. Okay, here it goes. Give it a second here and it starts. Okay, you can see what's happening. We're zooming in. We're going to be looking at that little piece there, right? And again, it's much thinner than this. Much, much thinner. But all I can say is it's extremely thin, this rope. And so if you have two of these ropes go through each other, because think of them as some of the properties that we have in our macro world, like if they were some kind of liquid or some kind of fluid of some kind, right? Then kind of blend and then keep going through, right? And that's the idea behind it. Those are the assumptions, okay? But why don't these threads blend with each other? Well, again, they're pulled sideways, by the ends. They're taut, in other words. Second, the assumption is that the thread is unbreakable in the sense of what we know, what our experiences are in our macro world. Everything breaks, right? And here, nothing breaks. The thread cannot break. You cannot break a thread. And you got to get that through your thick skull. You got to get that. You got to understand that or make that assumption, for otherwise you're not going to understand the theory. And it's not a question of believing. It's a question, do you understand it? And that's an assumption you got to make. You got to make the assumption that the thread is unbreakable, right? It twines around the other, but why doesn't it blend? It doesn't blend because they're pulled first in that direction, right, by the atoms. They're not pulled, but there's tension there, right? So it's like that. That's one thing. And then it doesn't have the speed. Right now, when it's just twined around, there's no speed going from one thread through the other. If there were speed, that thread would go through the other, but there's no motion of one thread going through the other, okay? And there's no speed. So those are the assumptions I make. I make those assumptions, okay? All I can tell you is the way I look at this, how my train of thought for that. And so that's what you got to think about. And again, if you say, well, I don't know about that, well, then that's when we bring Richard Muller again, and he says, every atom on Earth is connected to every atom of you, and you're pulling on it. You're pulling on atoms on the other side of the universe, the Earth, right now. And how do you pull without a mediator? So you have to put a mediator, and if you put a mediator, how do you avoid one mediator going through the other? You cannot. Not in a universe with so many atoms in so many different directions, right? Radially, right? They have to crisscross. There's no other way to avoid it. So yeah, the ropes go through the ropes. You don't like the ropes, you like field. The field goes through the field. Energy goes through energy. Mass goes through mass. Whatever you want to call that mediator, the ether, right? It goes through the ether. So, deal with it. That's all I can tell you. Deal with it. I had to deal with it. I went crazy on that, and I said, no, Mother Nature simply runs the universe like that. We have to understand that she runs a different universe than the one we have here in our everyday world, macro world. And that's what's confusing us. That's how she fooled us. We always thought that, the universe out there, if it's got something that's invisible, it ain't there. Well, there is something that is there, but it's invisible. Okay. How about tangible? Well, tangible, it's also intangible. And that's when people say, oh my God. Yeah, you have to make that assumption. There's no other way. I don't care what you propose. It's going to go through another one of those things that you propose. Field through field, energy through energy, whatever you propose. Wave through wave, yeah. Okay, so you got to get used to that. Otherwise, you're not going to understand our universe. Okay, and one fellow says, I find it quite weird that you don't like the concept of an invisible gravitational force, but you are completely okay with the invisible strings connecting the atoms. But yeah, let me tell you the second law of physics. Okay, we'll call it the second law of physics. I like law. It's a good word, law. I love the laws of physics. The mathematicians have their law that the laws break down at the singularity. Well, this one doesn't break down, the second law. All concepts are invisible. All concepts are intangible also. You can't touch a concept, and all concepts are invisible. What is force? Force is a concept. So you cannot compare it against a thread or string, as he called it, because a string, a thread, a rope, cable, fiber, all those are objects. Okay, and so you can talk about the visibility or invisibility of an object. All concepts, all of them, without exception, are invisible and intangible. Please deal with it. Okay, and so here we have another couple fellows, and they say, one says the following, we know the gravitational force between two objects decreases as the distance between them increases. Considering that your model for gravity is about tension in your ropes, doesn't that tension increase the further the distance between two objects, meaning the force of gravity would increase? So this fellow thinks it's an elastic band, a rubber band of some kind, so it stretches. And so the more you stretch it, the harder it is to stretch, so gravity should be stronger the more you stretch it. That's why, it's not a force, it's a tension. Tension is not a force like it is in the religion of mathematics, okay? What you have is tension, okay? The rope is under tension at all times. No one wins the tug of war. The atoms slide through the rope, and the rope itself, forms part of the atom. So it eats into the rope when it moves. So it's always under the same tension, which is given by C equals frequency times wavelength. That's why the velocity of light is a constant. It's a constant because if you raise the frequency, meaning the number of links for a given length of rope, right? Each link will be smaller. Wavelength, link length will be shorter. And if you untorque it, hey, guess what? The links become longer, but now you have fewer links. The frequency has declined. Okay, so only a rope can simulate the constant velocity of light, first of all, and second, it explains, gravity, because, it binds any two atoms, which is what the requirement that Richard Muller there exposed. And there you can see what's happening. The farther they are apart, the threads, the ropes all form a single coaxial, like if it were one rope only, because they superimpose, right? They're constantly falling into each other, okay? And they're stretched, not stretched, they're at large distances, they all come together. And when they're closer together, the ropes fan out. Eventually, there's an acceleration of gravity. Why? Because you have more and more ropes working or acting independently. And there you can see it at the bottom, if you what the mechanism is of gravity. You have a single atom on the cylinder, which is number 6 there, and all the ropes are on the same axis. And as the cylinder approaches, all the ropes fan out, and each one works independently. That's the acceleration of gravity, the number of ropes. And of course, the number of ropes at a given distance is weight. Okay, that's the definition of weight. Weight is not how many kilograms. Weight is how many ropes are converging at that location on that atom, one atom at a time. Okay. And another fellow asks the same thing, more or less. He says, all other atoms in the surrounding universe are also connected and pull. So they must be factored in the length distances, right? In other words, he's saying all the atoms close by, they got all these ropes, right? And so the length, the distance between them has to be factored in there, right? The pull in these threads must increase with reduced length. But how? Yeah, again, he thinks it's a question of elasticity, that the ropes are elastic, or the threads also are elastic that make up the rope. That's not the case. The ropes, you didn't, because if they were elastic, you would be creating new matter every time you stretch it. Where's the matter coming from? Are the ropes stretching? If they're stretching, where's the extra material coming from if there's a single thread in the entire universe? There's only one thread. And so, the answer is that the farther you go, the more they come together, the ropes, and because they come together, gravity is weak. And the closer you get to the object, the more ropes that separate, and that's the acceleration of gravity. That's the answer to those questions.